First years of here, and some of our folks from physics as well. Our first speaker for this academic year is Alex Drlica-Wagner from University of Chicago and Fermiland. Alex is not going to be with us. Actually, I learned today that he just did his undergraduate work at Washington St. Louis before getting his PhD at Stanford. He is one of the world's experts on using big wide field surveys, the sort of things that we care about here at Illinois, to understand the nature of dark matter. And he'll be telling us a lot about this sort of stuff today. I also learned very recently that we're trying to do a fun fact about each speaker. Okay. I didn't warn you about this. But I didn't learn about this recently. Alex, in his innumerable free time, isn't just a stunning astrophysicist, he was also a professional ultimate frisbee player. So should that be of interest to any of you, you can join in for dinner and then work it all off right afterwards.
I'm retired. Thank you. Thanks, Scott. Yeah, I am officially retired.
Post-ultimate.
Yeah, I'm post-ultimate, but I saved the paychecks because I have a 2-year-old son and I wanted to grow up and be like, your father was a professional athlete. The paychecks to prove it. The paychecks, by the way, were for like $500 a season, so it's kind of a very lucrative career, you may be surprised. Okay, so I'm going to be telling you a little bit about what's been going on recently in the search for some of the smallest galaxies. This background picture is from Cerro Tololo Inter-American Observatory in Chile. The big telescope you can see in front of you here is the Blanco telescope. It hosts the dark energy camera, a large digital camera that has been widely used by both people here, people at Chicago, who's built at Fermilab. And the target of study are going to be some of the smallest galaxies that we know of that are actually satellites of the Milky Way. And so from this site, by eye, you can see the two largest satellite galaxies of the Milky Way, the Large and Small Magellanic Cloud. We'll be looking at things that are 1 million times less luminous than these galaxies, about 10 million times less luminous than them. Okay, so the basic outline of the talk is I'll tell you a little bit about why you might be interested in finding and studying some of the smallest and faintest galaxies, and in particular, what they can teach us about the fundamental nature of dark matter, a mysterious component of the universe that makes up about 25% of the matter density. And then I'll tell you how we find these small dark galaxies, some of the constraints that we can get on the properties of dark matter from observations of these systems, where we're going next, and what observational tools are going to take us. So over a very wide range of scales, we've now measured the existence extremely significantly of non-baryonic components of the universe. So the ordinary matter, the protons, neutrons, electrons, neutrinos that are all around us make up about 5% of the energy budget of the universe. The other part is made up of dark energy, an expansive repulsive force, and dark matter, which for all intents and purposes over a wide range of scales acts as a gravitationally attractive, non-interacting component of the universe. We have measured it very significantly on scales from individual galaxies all the way up to the cosmic microwave background. And on these scales, the properties of the universe really follow very well a model called lambda CDM, or lambda cold dark matter. So dark energy plus some cold, non-interacting constituent of the universe. However, on a microscopic scale, we still have relatively little information about what dark matter could be. So there are a wide range of models. This is just a cartoon by Bertoni and Tate, showing classes, general classes of dark matter particle and less particle-like candidates. So there are things that you may have taken a physics class, heard about, sort of that have weak scale interactions, weakly interacting massive particles, or WIMPs. There are some macroscopic objects such as machos, which you might have heard of, primordial black holes, and particles that could have other mechanisms for interacting either with itself, so dark matter could be self-interacting, or it could have some interactions with the standard model at sufficiently weak or slow rates that they haven't yet been measured by our observations of the universe. So there's a wide experimental suite of tests of dark matter constituents. These occur often in particle colliders, particle accelerators. They occur deep underground where people build experiments and search for very rare interactions between dark matter particles and normal matter. But to date, the only positive empirical evidence that we have for the existence of dark matter comes from astrophysics. It comes from those measurements of the rotations of galaxies, the clustering of galaxies, the distribution of matter in the cosmic microwave background. And in addition, these astrophysical measurements are the only reason that we really have a bound on the allowed mass range that dark matter could take up. So we know that if dark matter is more massive than, say, a 30 solar mass black hole, that it would disrupt galaxies. Galaxies would be unstable if dark matter were chunked into constituents that massive. On the other hand, if dark matter was very, very light, 10 to the minus 21 eV or lighter, you would no longer be able to confine it to galaxies. So the de Broglie wavelength of dark matter, the wave-like characteristic of dark matter would be so broad that you couldn't pack it into galaxies. So already just from astrophysical observations, we're learning something about what dark matter can and cannot be. The real goal of this domain right now is to try and use measurements of the distribution of dark matter, where we see it in the universe, and what interactions it is allowed and not allowed to have, to learn about the composition of dark matter. So what kind of physical models are viable for explaining the existence of dark matter and its properties? So one very useful tool in these kinds of astrophysical and cosmological probes of dark matter is the matter power spectrum. This is a plot of the linear matter power spectrum. The lambda CDM conventional model is the black curve here. This is showing, in essence, the amount of clustering in the universe, the clustering of matter, as a function of length scale. So over here, we have measurements of the cosmic microwave background from experiments like Planck that measure the distribution, the clustering of matter on very large scales. Over here, we have galaxy clusters and large-scale structure of galaxies. And at the far end here, the distribution of matter as measured from the Lyman alpha forest from spectroscopy of distant quasars, which constrain the clustering of matter on small scale. And overall, the agreement with our standard cosmological model is quite good over a large range of scale. However, off the right-hand side of this diagram is where the smallest galaxies actually live. And in this regime, we have very few constraints on how the clustering of matter must behave. We do have some, and I'll tell you about those in the talk, but it's in this domain where we now have the ability to actually accept modifications to the dark matter, the particle physics of dark matter, which would then introduce changes in the clustering of dark matter. And so if we can measure the clustering of dark matter on these very small scales, we can tell things about, for example, the strength of interactions between dark matter and normal matter, or the thermal temperature of dark matter in the early universe, because these would make measurable changes, generally for these models, suppressing the amount of structure that we would see on these very small scales. So we can't measure, well, on these scales, we can measure dark matter directly, say by weak gravitational lensing. On these scales, the dark matter clumps, the halos, are small, and so the best way we have to probe them is through galaxies, the visible components that inhabit those halos. So one of our guiding pieces of information in this study come from numerical simulations. So I'm not a simulator, I'm an observer, but this is basically a snapshot, a picture of the motivation for why we would want to look at very small galaxies. So these are two suites of simulations. On the left-hand side, it's a simulation, numerical simulation of the clustering of dark matter in the standard cold dark matter paradigm. And you see a lot, this is a Milky Way mass halo, the big halo here. And you see a lot of structure within that halo. These are called subhalos, or substructures within the halo. And these are themselves expected to host small galaxies. On the other hand, these are alternative models of dark matter. One is a warm dark matter candidate, where the dark matter is produced with some thermal velocity in the early universe that suppresses structure on small scales. So you can see there are fewer structures in this simulation than there are over here. In this model, it's actually the dark matter is allowed to have some self-interaction. So it's able to redistribute momentum through dark matter collisions. And that ends up changing the distribution of matter as well. There are some small structures here. Actually, the main change here is in the radial density distribution of halos. So it takes them from very cuspy to very chord. It can also change, to some extent, their axis symmetry, their 3D distributions. So we can learn about dark matter properties by trying to measure the clustering of dark matter on these small scales. But these halos are not full just of dark matter. They also contain baryons, which go on to form stars, gas, dust, all of the normal stuff that we're familiar with in, say, our Milky Way galaxy. And that baryonic matter also can change the distribution of mass and the clumping of dark matter in the center of halos. What's really exciting right now is that over the last 10 years, there have been a lot of advances in high-resolution cosmological simulations, which are now able to include the core elements of baryonic physics on Milky Way scale. So you can run simulations and produce galaxies in the center of dark matter halos that have disks that look very much like the Milky Way. You can run it and produce satellite galaxies that look similar to the satellite galaxies that we see around the Milky Way. And so, in fact, we are now able to study both dark matter and the galaxy formation physics at the same time using these simulations. Yeah.
So as not a simulation person,
yeah.
Are you just having us on with DC Justice League being a group that does simulation?
No, it is indeed a simulation group. Allison Brooks is one of the people who runs it. Yeah. It started out with Marvel, and then I think DC Justice League is the successor to that, or maybe vice versa. But yeah.
But they would suite their own name after different characters.
Yeah, so right, so it's conventional in these numerical simulations to generate, a dozen realizations of a Milky Way-like halo, and each one, instead of getting a serial number like supernova, will get a name. So, like the Elvis simulations had pairs of Milky Way and Andromeda halos, and they'd name them like Bonnie and Clyde, Thelma and Louise, things like this, and yeah, they choose hero. In addition, these very small galaxies are also time machines. So by studying the star formation history of these galaxies, we can actually learn, these are very ancient systems. They form most of their stars in the first billion years or so of the universe. And they're actually some of the leading contributors to reionization of the universe. They're beyond, the smallest galaxies are well beyond the range of what we can study directly at reionization with JWST, but by studying their history of star formation, using the resolved color magnitude diagrams that we measure today, we can actually learn about the role that they played in reionization. Okay, so how do we find these galaxies that are 10 million times fainter than the Milky Way? All right, so we'll take a tour, and we'll start off with things you can see with the naked eye from space. So this is our Milky Way, halo mass of about 10 to the 12 solar masses, stellar mass of about 6 times 10 to the 10. Here's a large Magellanic Cloud, maybe 10% the halo mass, and the small Magellanic Cloud, which is another 10% of the LMC. These you can see by eye. the idea is that these satellite galaxies, the LMC and the SMC, inhabit some of the largest substructures, dark matter substructures that we see around the Milky Way. And our goal is to find what kind of dinky little galaxy will live in this small structure. So to do that, we use resolved stars. So these are galaxies, if we're interested in galaxies around the Milky Way, that's out to about 300 kiloparsecs. In order to find a galaxy like that, we have this very useful tool, which is the Hertzsprung-Russell diagram. So for a group of stars that are all at the same distance, you can sort them by color and magnitude or brightness. And what you'll find is this very characteristic sequence, which is an isochrone of a stellar population born essentially at a single time, which is true for these faint systems, where you have some main sequence that goes down a little bit below the mass of the sun. So these are 10 giga-year-old systems. So the main sequence turnoff is a bit less massive than the sun. You'll have a red giant branch and often a horizontal branch here. And so if you know the colors and magnitudes of stars in a field, you can specifically select those stars that are consistent with the isochrone of an ancient and distant, well, ancient and fairly distant galaxy, of order 10 of kiloparsec. So distant relative to the Milky Way stars, very close relative to any other galaxies you're interested in. In addition, once you see this isochrone, you can measure properties of the system, such as its age from the position of the main sequence turnoff, its distance from the apparent magnitude, and the metallicity from the slope of the red giant branch. So as the first step, we use this essentially as a very simple filter. The actual method we use is a bit more complicated than this, but this gives you a pretty good idea of how it works. So you start with a stellar field, it has an ultra faint, very small galaxy hiding within it. Once you filter the stars based on color and magnitude, you can get rid of a lot of the Milky Way foreground. And what you end up with is some density, overdensity here. If you then convolve that with a spatial kernel, this is your detection. And this is actually, I think, the ultra faint galaxy Ursa Minor. Actually, no, maybe Ursa Major too. They're all named after the constellation they reside in. This was perfectly great when there were about 12 of these. It's becoming problematic now that we have more than 60, but that's the context. And so you can run this on a single stellar field, which is what people could do before the advent of large surveys. With the advent of SDSS, you could start running this over thousands of square degrees of the sky all at once. And this allowed you to find galaxies like this. This is the Segway 1 ultra-faint dwarf galaxy. It has a stellar mass of about 340 solar mass. Yeah.
So on the previous slide, that wasn't the discovery of that galaxy. That was the validation. This technique works to really something we already knew.
This is real data on one of the ultra-faint dwarf galaxies that was discovered in SDSS. This is not Segway 1, but it is an ultra faint. It's a little bit brighter than Segway 1, but Segway 1 is detected at like, I don't know, 15 sigma or something like that. Yeah.
340 solar masses per galaxy. What is the difference between a ultra faint dwarf galaxy and a globular cluster then? How do you
Great question. Okay, hold on to that question for a few more slides. Yeah, that's a great one. So the first question is, how do I even convince you that this is a galaxy? Right? So you don't see anything in this image, right? It's not the projector. The fact is that this galaxy is made up of individual faint stars. They're distant, that's why they appear faint. It's at like 26 kiloparsec, something around that. The way you convince yourself that this is in fact a coherent system is you go out and you measure the radial velocities of the stars in this part of the sky, and you find that they're all moving through space together and at a very different systemic radial velocity from the rest of the Milky Way stellar distribution. You usually measure these with things like the calcium triplet lines. You can go out to Keck or use IMAX the Magellan telescopes to make these kinds of measurements. Or nowadays you can use DESI, which is a large spectroscopic instrument. In order to convince yourself that this is not a globular cluster, what you're interested in doing is measuring the dark matter content. So in the mid-2000s, I think 2010, there was a proposal from Beth Woman and Jay Strader to actually come up with a definition for what a galaxy was. And their proposed definition was that it was a group of stars where the dynamics could not be purely described by the observed mass, Newton's laws of gravity alone. In other words, a galaxy is stars inhabiting a dark matter halo. It doesn't matter how many stars, that was an interesting part of their definition. It's really the presence of the dark matter halo that binding them together that's important. So if you want to claim that that thing is a galaxy, you need to go out and you need to measure the dynamical mass of those stars. So the stars are moving through space pretty much together, but they have a velocity dispersion of order a few kilometers per second. The stellar mass that you have there is about 1% or maybe even less of the mass you would need to have a system bound with that dispersion. And in order to make that a bound system, you need 100 times more matter in it than what you can see in stars. And so if you go out and you measure these velocity dispersions, so the width of the histogram here of the stellar radial velocities, you find that these systems have 10 to 1,000 times more mass in them than can be observed with their star. You go out and try and observe gas and they're completely devoid of gas to the extent that we can measure. So this is how you convince yourself that what you found is actually a dwarf galaxy. Star clusters in comparison have mass to light ratios of that.
And the inference that they're bound has to be related to the age, the dynamical age.
So you relate it to the dynamical age, but you also look for any indications of extratidal features. And in the dwarf galaxy, the ultra faint dwarf galaxies, you don't see them. In other systems, you see them being tidally disrupted. And then this doesn't work, right? If they're being tidally stripped apart, then yeah, you can't make this assumption. So before you measure the radial velocities, you may have a hunch for whether something is a dwarf galaxy or a star cluster. And that hunch is generally based on the morphological properties. So as of the end of SDSS, we had this fairly nice divide between dwarf galaxies and star clusters, where the dwarf galaxies end up being maybe a factor of 10 to 100 larger in half-light radius than the star cluster. And this is just another indication of more binding mass to hold them together, right? So more mass allows them to actually be larger at a fixed luminosity. And so people would guess, basically draw a dividing line here and say anything larger than, I don't know, 20 parsecs, we can say is a candidate dwarf galaxy, anything smaller is a star cluster. But you don't know that for sure until you measure the dynamical mass. So at the end of SDSS, this is what our population of ultra-faint dwarf galaxies, satellite galaxies around the Milky Way look like. From photographic plates in the first part of the 1900s, we found about 12 what are called classical satellite galaxies. And then SDSS had turned on, and using this statistical match filter isochrone finding had doubled that population. The predictions from simulators at the time were that the total population of Milky Way satellites should be larger than that, of order hundreds to 1,000. If you applied selection effects, which people were starting to do then, basically accounting for the fact that not every satellite galaxy was expected to be comparable brightness to the brightest ones that we had discovered previously. In other words, assuming there was a large population of faint satellites, CDM was making predictions that with the next generation of surveys, like the dark energy survey, we should detect of order 40 to 50 satellite galaxies around the Milky Way.
How do you normalize this? I mean, SDSS only sees effectively you have those guys.
I will get to that.
Okay.
Yeah. So this is just hand waving, but we do it rigorously, and I'll talk about that.
And do the mesonetic clouds, they're
They're more massive than me.
Yeah, they're out here.
Okay, there.
So this starts at 2.
Yeah, they can, okay, yeah.
And then also, in terms of predictions, were they predicting satellites to be 300 mass galaxies, or were they thinking like 10 to the 4?
Correct. So this is a big issue, and I don't want to talk about it a whole lot, but for a long time, there was something called the missing satellites problem. The missing satellites problem was basically taking that picture that we saw before, where there were those simulations with like 1,000 small dark matter clumps in the simulation. And if you put a galaxy that's LMC mass in every one of those subhalos, then you have a real problem, because we would have seen 1,000 LMCs around the Milky Way, and we didn't see that. So people needed to make some, before SDSS began, there was no observational evidence for this. So people would say, well, we only see 12 galaxies, but we expect 1,000 subhalos. What's going on here? Is lambda CDM broken? Is our understanding of galaxy formation broken? Are we just missing a bunch of galaxies? And so in order to do this modeling properly, you both need to have a model for how galaxies populate dark matter halos, and your observational sensitivity to galaxies as a function of their properties, their size, their distance, their luminosity. And so the missing satellites problem was basically, I would say it was a catchy phrase that was really neither side, neither the simulation side believed that every subhalo should have a galaxy, and the observational side didn't believe that we found all the galaxies. So it caught on, but it wasn't as much of a real problem as it is. And I think by now that's sort of a spoiler. Okay, so at the end of SDSS, we had that population of about 24 satellite galaxies, and along came the dark energy camera on the Blanco telescope. This is a 4-meter telescope in Chile. And one of the first projects that it was used for was the dark energy survey. This is actually what the dark energy camera was built to do. And there are a lot of people here that were very involved in this, and all of the data management project was led by NCSA here. And so just to give you a sense, this is the same region of the sky observed with SDSS, and this is with DES. So you're going about 10 times deeper in your DES imaging than you were able to go with SDSS. And the other thing that's really amazing about DES is its photometric calibration. So it has calibration accuracy of about 2 millinags in spread. And for comparison, if you transform from the DES magnitudes to the Gaia G-band magnitude, and Gaia is a space-based mission, so it doesn't have to look through the atmosphere, it doesn't have to deal with clouds or anything like that. The residuals that you see are showing very strongly the Gaia scan strategy. So Gaia is actually, the Gaia photometry is the dominant uncertainty in this comparison, not DES. And this is important because it allows you to measure those isochrones, those color magnitude diagrams, really precisely. And so that allows you to do a really good job of selecting stars that are likely to be associated with ultra-faint dwarf galaxies. So here's an example of a galaxy that we found with DES. At this point, I think you're used to not being able to see much of anything by eye. However, you can go and you can do deeper follow-up imaging, and this is what the color magnitude diagram looks like in DES. This is a pretty strong and significant spatial overdensity. If you go and do deeper imaging with the Magellan telescopes, and this was a project led by one of the postdocs in Chicago, pristine, you can get way below the main sequence turnoff and actually see a very prominent main sequence down there. So these systems are very much real. They're being detected at 5 sigma in DES. They look very suspect, but you go and follow them up, and these are real systems. So this was at the beginning of, at the end of SDSS. These are predictions of lambda CDM, assuming no missing satellites problem. And here's the satellite population that DES found. It's completely consistent, but as Joaquin pointed out, I'm not doing any selection effects built in here. So the CDM predictions assume some model of galaxy halo mapping, and they assume the DES footprint shape but they were made well before the DES data ever came along. By eye, though, the consistency appears to be there. Yeah.
Remind me what the distinction is between the too big to fail problem and the satellite problem, and did this also solve that?
The too big to fail problem is slightly different. It's about the central densities of the dwarf galaxies. And so there it's saying that we don't have enough massive dwarf galaxies, rather than the missing satellites problem, which is about counting all of the dwarf galaxies. This doesn't quite solve that problem. That problem we can talk more about, but there have been suggestions that baryonic feedback and baryonic mechanisms may push mass out from the central regions of dwarf galaxies, lowering their central concentration for the most massive dwarf galaxies. For the ultrafaints, that shouldn't be at play, but there are so few stars in the ultrafaints that it's very hard to measure their central density. So I now have dots that are different colors. The red ones are ones that we've been able to go out and make the dynamical measurement and confirm that they are indeed dark matter dominated galaxies. The sort of light red dots are objects where we've gone out and we've taken spectroscopy, we've confirmed they're real systems, but we don't have enough stars to measure the dynamical mass well enough. It's consistent with being a dwarf galaxy, but we don't have a lower bound on the velocity dispersion. And the white dots are systems that we haven't been able to get spectroscopy for yet. This has led a lot of work by collaborators Ting Li and Gus Simon. Okay, so now to do this comparison rigorously, what we need is to do a census of the dwarf galaxies, accounting for all of the selection effects in our survey. So what we did in 2020 is we took this, basically the current coverage of observational surveys at the time, which is dominantly from pan-stars in the northern hemisphere and from DES in the southern hemisphere. We came up with models of satellite galaxies, and we injected simulated satellite galaxies into our data and ran our pipeline to recover them. And by doing this a million times, we were able to very rigorously pin down what properties, whether a dwarf galaxy would be detected or not, given its properties. The properties that were dominantly important were the luminosity, the size of the dwarf galaxy. The larger it is, the harder it is to detect, because the lower the surface brightness, the harder it is to distinguish the clump of stars in the dwarf galaxies from the background distribution. And the distance for the dwarf galaxy is important. So with this observational selection function in hand, we can now go to those M-body simulations. We can select simulations that look like our Milky Way, including the existence of an LMC. We can take the dark matter halos and we can paint galaxies onto those halos using a prescription for how stellar mass correlates with dark matter halo mass. We can generate a simulated population of satellite galaxies and then apply our selection function to know which of them would have been detected or not. Then we can calculate an agreement statistically between the simulated population that we get and our observed population. And then we can do this as a loop, right? So we can run this in an MC-MC chain where we change the galaxy to halo mapping prescription. We change, how the stellar mass maps onto halo mass, at what point galaxies stop forming in halos, all of these different parameters, and basically constrain at the same time the properties of galaxy formation and properties of dark matter physics. And so the prediction that we get from a lambda CDM simulation model with these prescriptions for galaxy formation are perfectly consistent with the observed data. So this means that we can model the observed data with lambda CDM without needing to impose any modification to dark matter physics. And this is basically recasting and saying there is no missing satellites problem. We're perfectly fine putting galaxies into dark matter halos and reproducing the observed satellite distribution that we have. One interesting thing that we found is that there is a large overdensity of satellites in the DES footprint. So DES is deeper than SDSS, But accounting for that added sensitivity, you still see more satellites in this part of the sky than you would expect. This is not completely unexpected, because this is the region where the LMC and SMC exist. And going back to the 70s, it's been proposed that the LMC, and to a lesser extent the SMC, should have come in with their own populations of less massive satellite galaxies. And so we're now detecting this at the level of several sigma, something like 4 sigma in the population. And what it means is that in order to accurately compare the observed satellite population to simulations, your simulations need to include an LMC, because these satellites can be of order 30% contribution to the observed satellites. They're preferentially located at small distances. The LMC is 50 kiloparsecs away. Its satellites are also closer. And so they are can be a fairly large contribution to the observed satellite. Yeah.
Are the LMC and SMC sitting in a subhalo then, and everything else is sitting in like a subhalo?
Yeah. So the LMC and SMC each sit in their own subhalo, and they would have satellites of satellites, yes, that came in with them. Whether those satellites are now still bound to the LMC seems unlikely. They from the dynamics of these satellites, it's hard to find one that I don't think any of them have been conclusively determined to still be bound to the LMC. So they were ripped off by the Milky Way. They're now Milky Way satellites, but they live in their own.
I have to follow up.
Yeah, how are we doing on time?
No, it's really interesting. Oh, I can wait until after.
Yeah, I think I should go. Okay, so this causes an issue, right? If we need to compare to simulations that include an LMC, if the LMC is biasing the distribution of Milky Way satellites, it means that it's important to also study satellite galaxies around isolated hosts. And so another avenue that we've been exploring in DES and other surveys is actually the detection of low surface brightness and ultra diffuse galaxies around other nearby galaxies in the local volume. And so here are some examples of low surface brightness galaxies. This is around, it's near to one of the hosts that we have that we're doing follow-up imaging of, but I forget which one. So anyway, I think LSST is going to be remarkable for this kind of science and increasing our knowledge of the satellite populations of isolated galaxies in the local volume. When you look at these things, it's very interesting. You see multiple populations, blue LSTGs, red LSTGs. This is this was a paper from a few years back, but this is a lot of ongoing work with the dark energy camera to try and really map out the distributions of these faint unresolved systems in the local volume. You can see if you divide on color, the red systems are much more highly clustered than the blue systems, and you can see structures like this is the Fornax galaxy cluster here, right? So you're seeing local structures in this distribution, which is telling you something about how these low surface brightness galaxies are forming as satellites of more masses. Okay, so I said that CDM is perfectly capable of reproducing the observed distribution of satellites around the Milky Way. So what does that teach us about dark matter? What can we learn about dark matter properties from that? So what we're looking for, just to remind you, is because the black line here, the CDM model, is a good fit to the observed satellite population, we want to see how much we can change this model before the predicted satellite population becomes inconsistent with the observations. And that then allows us to constrain that model of dark matter physics. So I'll just step through quickly a few of the different kinds of dark matter models we can constrain. So the first one is sterile neutrinos. Sterile neutrinos have can have a number of different production mechanisms. Some of the most conventional production mechanisms produce sterile neutrinos with a warm momentum distribution in the early universe that suppresses the formation of structure at early times and would lead to a suppression in the number of satellite galaxies that you would see. So by running the same MCMC chain and now allowing an additional free parameter, which is a suppression of the matter power spectrum, you're able to constrain resonantly produced sterile neutrino dark matter to be more massive than this red line here. So this is 50 keV down to about 20 or 30 keV here. And so this actually does a pretty impressive job of constraining an interpretation of an X-ray line that was some groups interpreted as to be potentially a signature of decaying sterile neutrino dark matter, assuming that it's resonantly produced with the thermal velocity distribution. Yeah, Bill.
So are these all confirmed to be galaxies according to that definition?
So that's a good question. So not all at the time we did that have been confirmed as satellite galaxies. So there's one right in this map that has not been, and a few that are consistent, but have not been confirmed yet. They lie far on the, I'll show you where they lie in the size luminosity space. They look very much like galaxies. Yeah, so. Another thing you can constrain is fuzzy dark matter. This is a model where you have ultra light dark matter particles where the de Broglie wavelength actually becomes larger than the size of the galaxy. If that happens, you can no longer produce small halos and you can't produce the ultra faint galaxies. So again, you suppress the matter power spectrum and you suppress the number of galaxies that are predicted. And by comparing that suppressed galaxy distribution to the observed galaxy distribution, you can constrain the properties of dark matter to be heavier than a few times 10 to the minus 21 eV. And there have been further arguments since we did this that actually argue that another property of the dark matter distribution, basically these transient features, granules that arise from wave interference, would actually disrupt the dwarf galaxies before in a more severe way than just this suppression of the matter power spectrum. And then the final one is basically just generic models where you have dark matter that interacts with the standard model. So you're able to exchange energy between the standard model and the dark sector and dark matter. This has the effect of heating up the dark matter in the same way that sort of thermally produced warm dark matter would be heated and suppressing structure. And this then allows you to constrain the cross section. This is the spin independent scattering cross section between dark matter particles and the standard model. And if you look, these are actually some of the particle physics experiments. These are the upper edge of the some of the particle physics experiments that are similarly looking for these types of models. They cut off at the top here because dark matter would be scattering in the atmosphere or in the rock and never make it to where these experiments are located. Okay, and then there are other constraints. In the end, the generic way that we would like to do this is really to set more constraints on the matter power spectrum at small scales. And this is a first attempt to do this. This is from a group led by Annika Peter at OSU. And it's really the blue contour here is their interpretation of the Milky Way satellite population constraint on the matter power spectrum.
But do you have plans to follow that up in, whichever experiment is?
Yeah, so Ruben LSST will put more contours on here, and we are
using this technique. This is the velocity, so they're using a velocity dispersion.
So yes, there is using a velocity dispersion measure, and they're using only SDSS. In doing this, so it should be possible to expand. Whether I'm the right person to do this or not, I'm not sure. Yeah. Okay, so the CDM model makes this fairly generic prediction that that halos should continue to exist to almost arbitrarily low masses. However, in order for galaxies to form, they need to survive reionization, so they need to be in gravitational potentials that are deep enough to retain the gas in order to be able to form stars. So at some point, at a halo mass somewhere in the range of sort of 10 to the 7 solar masses to 10 to the 8 solar masses, we expect the efficiency to form galaxies in dark matter halos to turn off. At which point dark matter halos would continue to exist, but they would no longer host galaxies. And so these halos can't be probed by counting the number of satellite galaxies. So there's a big question of how do we detect these completely dark matter subhalos, which are a strong prediction of both the dark matter model and lambda CDM. So here's an analogy. So this is an image, I think from Cassini, of one of Saturn's shepherd moons. These are 2 of Saturn's rings. And I would argue that you would be able to tell me that something was going on here, even if you weren't able to see that moon. So the basic idea is that the gravitational interaction of the moon with the rings imparts visible features in the ring. And one of the techniques that we had that has been proposed for the ability to detect completely dark matter subhalos uses the same basic idea. We're going to use a tracer that we can see and look for gravitational perturbations that are imposed by things that we cannot see. So our observable tracer are called stellar streams. They're the tidally disrupted remnants of satellite galaxies and star clusters. They form over gigayear timescale as these systems orbit around the Milky Way. The stars are spread out along orbits, and they're fairly fragile. So they're not dynamically bound. And so if these stellar streams are impacted by a floating dark matter subhalo that's bound to the Milky Way, then it will impart some kind of gravitational disruption to the stream. So the way that we find these streams is very similar to how we find the satellite galaxies. This is the color magnitude diagram of a globular cluster NBC 1904. This is an isochrone filter that's being passed over the stars in a region of the sky where this globular cluster resides. And you can see when the matched filter matches the color magnitude distribution of the globular cluster, you get a sharp peak in the intensity of stars, so the density of stars. So people have been using this technique since SDSS to measure extratidal features around globular clusters, but the calibration of DES is so good that you can really run it en masse over the entire DES footprint. So that's what's being done here. This is a 5,000 square degree footprint of the dark energy survey. And I'm running a color magnitude filter similar to the one that was shown on the previous slide over this. And all of these structures that you see pop out here, these linear structures, are either sort of stellar streams here and here, there. You see some extratidal features around globular clusters. All of this is essentially walking out through the stellar halo of the Milky Way. Yeah.
So this is awesome, and also you didn't use any fancy words like machine learning
No.
to do this. So how did this very physical and kind of straightforward and interpretable method compare to all these kind of fancier stream binding algorithms?
So I think, so I would say,
I was hoping.
yeah. So Matt Buckley and crew at Rutgers have been very interested in applying their fancy machine learning algorithms to this. Generally, they're also using proper motion information from Gaia. I would say that, in my impression, is that the verdict is a little bit out there, because really what you want, you have physics knowledge, which is that stars are on orbits and they behave, they obey Kepler's law, right? They obey Newtonian gravity. And it's hard to teach the machine learning algorithm that. But the machine learning algorithm is extremely good at finding clusters or outliers in these distributions. And so my understanding right now is that the two groups, that basically these two approaches come up with some shared stellar stream candidates and some differing candidates. And probably it'd be interesting to follow up on all of them. With DES, we generally are going farther away into the halo than Gaia is able to detect. And the reason we're able to do that is because we've got a larger telescope and we've got this really precise photometry, but we don't have proper motion, so we don't know the orbits. I had a student run YOLO, which is like this regional CNN type algorithm to try and just, it's like one of those things of find faces and images kind of thing. And it could pick up some of these, it picked up a bunch of false positives, and then the summer was over. So, so for these streams, you generally can't detect them. You can't discover them with Gaia, they're too far away. But once you know where they are, you can identify a few stars in Gaia that belong to the stream and use that to measure the systemic motion of the stream. So how it's moving. And if the streams are not perturbed, if they're just going around in normal gravitational orbits, you expect the motion of the stream to be aligned with the track of the stream. So basically the stars are moving along this orbit, their motion and the direction of the track are aligned. What my former student Nora Schiff found was that in fact, there are a lot of these streams where they're being tugged off of their track. So their proper motions are actually misaligned with their track direction. And this appears to be correlated with the infall path of the Large Magellanic Cloud. And this you could expect, though I don't think anyone had predicted this before the observation was made, but the LMC is this huge, massive perturber falling into the Milky Way. It's gonna tug on systems that are in orbit around the Milky Way. And so you can turn this around and try to use the measurements of how much each stream is being tugged on to estimate the mass of the LMC. And through this technique, Nora estimated a fairly massive LMC. So this is like 11.5 solar mass LMC, which is consistent within errors with some other estimates that are coming from the Sagittarius stream or Dwarf stream. But I think there is sort of this consistent picture coming together that the LMC is a fairly massive perturber around the Milky Way. What we're interested in doing is measuring much smaller scale perturbations, right? We want subhalos that would be impacting streams and leaving discrete gaps rather than an overall tugging of the stream. So it is, there have been several groups that have looked at individual streams and seen evidence for these gaps. And even come up with models for the perturber masses that would be needed to introduce these gaps. However, often when this fit is done, you end up needing a perturber that at this mass is much more compact than you would expect for a lambda CDM NFW halo. So more concentrated halos. We do know of more concentrated objects in the halo of the Milky Way. They're called globular clusters. And they could similarly introduce some of these impacts. But we have a pretty good idea what the population of globular clusters looks like. What we really need to do is measure a statistical sample of gaps and compare it to models or what the impactor scenarios would be for a CDM for dark matter halos versus the known baryonic. And so this is work that's starting to be done sort of en masse. This is one of the streams. This is the Phoenix stream. You can see that there are some gaps in it here. You can measure the density of streams along their tracks, and you see that they have a lot of density perturbation. But I think it's still very early days in going from these kinds of density measurements to actual, constraints on the subhalo population, because we don't have a really good handle on what the baryonic expectation should be for the stream density variations. And there are a lot of dynamicists working really hard on this. And there's a lot of data that's going to be coming along to make these measurements even better. I think in the end of the day, it's going to be very hard to measure dark matter halos without any baryons in them, but it's like a very fundamental test of lambda CDM, and it's very much worth doing if we can do it. Okay. So how am I doing on? All right. Okay, so what have we been doing more recently? Well, the dark energy camera was used originally for covering the dark energy survey, which is 5,000 square degrees here. But over the last, at this point, 4 years, almost gonna be 5 years, we've continued to use DCAM to cover as much of the rest of the sky as we can. And so at this point, we now have coverage of more than 20,000 square degrees of the sky in GRIs. Our second, so this is a project that I've been pursuing with a number of different collaborators. It's called the DCAM Local Volume Exploration Survey. Here's a handful of them. We have a number of different program components. The original survey was proposed to be a study of satellite galaxies around the Milky Way, the LMC, and some nearby local volume analogs. But all the data is public and all the data is broadband imaging data, so it can be used for a whole wide range of different scientific studies. And the data, the raw data are public immediately, and the process data come out as basically as fast as we can. So we've had 2 data releases so far. So over the wide area survey, which is here, we're looking at dwarf galaxies and stellar streams. This region is about 15,000 square degrees, but since then we've added regions up here that were covered by decals to increase the area. We're also looking around the Magellanic Clouds. We have deeper data here, as deep as DES. In this region, we're about as deep as 2 years of DES's 5-year survey. And then we have 4 small galaxies in the local volume at distances of about 2 megaparsecs. They're roughly Magellanic Cloud analogs in isolation. And so our hope is that we can measure their satellite populations and use it to inform things about the LMC and SMC satellite populations, which have all been mixed up into the Milky Way and are hard to measure directly. So in data release 2, we covered about 20,000 square degrees, 2.5 billion objects, and coverage in GRI and Z. We found a number of satellite galaxies and faint star clusters, and these are really interesting objects. I'll say a little bit more about them. So at this point, the satellite galaxy timeline looks like this. We are adding more and more objects that we don't have confirmed spectroscopy for yet, but we're trying hard to get it. And we're not the only game in town. There's also Pan-STARRS discoveries, Cypress Prime Cam has been discovering things, Atlas and Gaia. So if this is what our diagram of size versus luminosity looked like at the end of SDSS, the area down here was largely unexplored because it was too faint for SDSS to find things. Here's what the observed population looks like now. We've pushed down in surface brightness by, I think, I don't know, this is 2 magnitudes, maybe 1 or 2 magnitudes. And we're also starting to discover a number of systems in this very small half-life radius region. These systems, it's very unclear what they are. The predictions really break down both on the satellite galaxy side and the star cluster side. And we really can't get dynamics for a lot of these until we have 30-meter class telescopes. They're just too distant, too faint, too few stars to go after with, say, Magellan. From the simulation side, these are some of the state-of-the-art high-resolution hydro simulations. These are our systems. They're orders of magnitude smaller and less luminous than what are, the highest resolution simulations are predicting. However, if you go to sort of semi-analytic models, there are actually predictions that dark matter halos could be populated by satellite galaxies with comparable size and luminosity. So I think this is still a very open question. What are the nature of these systems? Are they any even more faint, like a hyper faint population of satellite galaxies? Or are they just undermathed globular clusters? We don't know. In addition to doing this near field cosmology, we can also do far field cosmology with DELV. We can look for strong lenses. This is another very big machine learning, popular machine learning task. Looking for background galaxies that are being lensed by foreground galaxies, another good probe of dark matter physics. And we can try and do large scale structure cosmology. So this was a proposal that we got awarded to try and do weak lensing cosmic shear measurements using the Delft data. And this is the data processing is being heavily supported by NCSA. So as time goes forward, we keep pushing to fainter and fainter systems. The next thing on the schedule is Rubin LSST. This should allow us to detect the faintest known satellites out to the edge of the Milky Way halo. And the predictions for LSST range a bit. Each of these stars is a prediction for what LSST should see. But overall, the idea is that we should be detecting hundreds of order 200 satellite galaxies with LSST. In black here is our current measurement, which I'll remind you is consistent with CDM. And so this gain is really coming just from the increases. In order to measure the dynamics of those systems, however, we're going to need big telescopes to measure radio law. So that's it. Sorry for running long, even though I'm sure I did. The summary is that dark matter is a huge open question. We should use astrophysics as much as we can to try and answer it. And the small galaxies are a great way to do that. So thank you.
We have time for some questions.
So at what point do you stop getting satellites and satellites? Like, what is the smallest satellite that can have another satellite?
Okay. So you could answer this question in a statistical basis, but I think the more fundamental question is what's the smallest mass halo that can host a satellite? And we don't know for sure yet. We haven't seen a strong indication for that cutoff yet. We expect though that it's around between 10 to the 8-ish and 10 to the 7-ish solar mass halo. And then those could be subhalos of Milky Way mass halos. They could be subhalos of smaller mass satellites of the Milky Way. Yeah. Lambda CDM predicts that there should be subhalos of.
You said that you need to see the dark matter halo. Will you investigate further the dark matter density profile or no?
Yeah, so that's a great question. So yeah, Lambda CDM makes another very strong prediction, which is the radial density profile of dark matter halos, that it should be very cuspy in their inner region, go like R to the -1. So with the galaxies that we've been discovering, there are not enough stars with spectroscopy available. And in some cases, there are not expected to be really enough stars in the system to be able to get very precise measurements of the halo density profile. For some of the classical dwarf galaxies, people have been making this measurement. And what they have found is that for some of the most massive satellite galaxies, the dark matter halo density doesn't appear to be quite as cuspy as you would expect from Lambda CDM. This is in part the too big to fail problem. And one of the explanations that's been given is that as you form stars, you're basically through feedback, you're pumping the mass distribution in the inner region of the halo, and that smooths out and cores the dark matter halo. So it may be that baryonic processes are suppressing the dark matter peak, or maybe dark matter doesn't have a peak. Yeah.
If there are no other questions. So you talked about looking for basically the cutoff in the matter power spectrum. So I know of a couple of ways, only one of which is actually in the literature yet, to actually provide an enhancement on small scales. What would that? I presume it would be easier to see.
Yes, yeah. So actually, the Esteban paper
Yes.
did this, and they called it something like lumpy dark matter. Their enhancement. I don't know that you could tell me whether or not the model is well motivated. I'm not sure. The issue with the prediction side is that in order to, so the way we map from the linear matter power spectrum to the highly nonlinear distribution of galaxies is through running these numerical simulations. As you increase matter power spectrum at small scales, you need higher resolution to run your simulations rigorously. So it becomes more computationally intensive. And I don't think the simulators have really tackled that question in the rigor that they have tackled
For
the
sure.
suppression question. So that is one of the caveats that I would have for this one.
Yeah. Great, thank you.
So I guess you focused a lot on the Rubin side of things, but how does Euclid help you here, especially if you have extra color information in the infrared, and you can see each of the things that it does? Does it make sense to also think about giant pixel processing between Rubin and Euclid?
So I think the main place that we've been thinking about, or the main two places we've been thinking about the space-based observation, one is star galaxy separation. So as you go to fainter magnitudes, you get a lot of unresolved blue galaxies. And then the other one is proper motion. And so we've been thinking, I think, a little bit more about Roman, which is deeper than Euclid. But I think
Much smaller and wider.
that's right.
Any other questions?
And there may be some answer.
Oh,
Is there any questions?
I see a question from Brian and then with Stu. So can we go in that order? Brian, you guys can unmute and just speak up. He should be able to hear you.
Okay, Alex, thanks. That's really beautiful stuff. So we talked about this a little bit, but how about metallicity? So for the dwarf galaxies, one of the things is, convincing yourself you're not seeing a globular cluster. How do the metallicities compare to globular clusters?
Yeah, so there's generally a strong mass metallicity trend. So as you go to low masses, you go to low metallicities. The systemic metallicity for some of these ultra-faint systems is like Fe over H of -3. So 10 to the 3 times more metal poor than the sun. And the globular clusters both can also go to these very metal poor regimes. There has for a long time been proposed that there's a metallicity floor on globular clusters, but I think over the last few years that has been broken in a few ways. One way being the globular cluster stellar streams, some of them are extremely metal poor. I'd say the main difference is in the metallicity dispersion. And so if you're able to retain supernova ejecta, you can have some ongoing star formation and get a wider range of metallicities. And that has been used as one piece of the puzzle in distinguishing dwarf galaxies from star cluster.
That's nice, thanks.
and Steve?
Yes, one distinction between star clusters like globular clusters and small galaxies is that star clusters have little or no dark matter, unlike many of the small galaxies. What's the current thinking on how this distinction comes about physically? It's a question I've been looking into.
Yeah. So in the broadest picture, the basic idea is that the dwarf galaxies are forming primordially in dark matter overdensities, at early times, whereas the star clusters are forming within galaxies in molecular clouds and other baryon-rich system. And so you also see this hypothesis is borne out also in things like the radial distribution of globular clusters, which are much more centrally concentrated, whereas the satellite galaxies are an accreted population. Hopefully that answered the question somewhat.
Well, that's a good candidate. Thank you.
Yeah, okay.
Awesome. Well, if we don't have any other questions, let's thank our speaker again. Like this, speak more with Alex, or in this case, actually, it's a special dinner because we have 2 other visitors in town from Chicago, Abby Varig and Ty Figueroa, who will also be joining us for dinner. Then leave me outside at 5:30, and we'll figure out exactly where we're going. Head out from there.
Thanks, Alex, very cool.
Thank you.
Thanks, folks.